Ladies and gentlemen, welcome back. Before commencing to the PM session today, we would like to announce the results of the Fire Engineering Excellence Award 2022. May I now invite Engineer Learn Kun Hon, the Chairman of Organizing Committee of Fire Engineering Excellence Award 2022. Engineer Learn, please.
Dear fellow professionals, thank you again for joining the Fire Symposium 2022. Taking this opportunity, the Fire Division would like to announce the results of the Fire Engineering Excellence Award 2022. The objectives of the award are to develop the fire engineering culture in the industry, to recognize fire engineering professionals, developers, building owners, project teams for their remarkable achievements on fire engineering designs and researches, and to provide an avenue for sharing of fire engineering knowledge, experience, and practice. Before announcing the results, I would like to say thank you to the members of judging panel. They are Engineer Andy Yeung, Director of Fire Services, Ms. Karen Zhang, Assistant Director of Buildings Department, Professor Richard Yun, Head and Professor of City University of Hong Kong, Engineer Professor Chen Xiulai, Chair Professor in Computational Structural Engineering at the Department of Civil and Environmental Engineering, the Hong Kong Polytechnic University, Engineer Erwin Zhong, President of the Hong Kong Institution of Engineers, Engineer Paul Chen, Discipline Representative of Hong Kong IE Fire Discipline, Engineer Professor Daniel Low, Division Chairman of Hong Kong IE Fire Division. This year, the submissions were all of excellent quality and represent very high standard of works. After the judging panel's critical assessments, they decide 1 grand award, 2 commendation merit awards, and 2 finalists. Here comes the results. The finalists are Hang Yunwei Boundary Control Point, Passenger Terminal Building by WSP, Shenzhen Qianhai Transportation Hall by Arrow. The commendation merit awards are ASI by Arrow, Eastern District Advanced Medical Center of Hong Kong Sanitarium and Hospital by Arrow. The grand award goes to the Hong Kong section of the Guangzhou, Shenzhen, Hong Kong Express Rail Link, Hong Kong West Kowloon Station by MTR Corporation and AECOM IDAS joint venture. Great congratulations again to all winners. In order to express their gratitude, our grand award winner has prepared a video to say a few words for us. Thank you.
多謝評審委員頒予高速鐵路香港西九龍站呢一個消防工程卓越大獎。咁當然覺得好高興啦！呢次嘅參賽團隊咧係由港鐵公司帶同顧問 AECOM IDAS 組合而成嘅。喺呢度，我代表 MTR 再次多謝主辦單位香港工程師學會消防分部。跟住落嚟，都等我哋顧問分享下得獎感受啊！
大家好，我係 IDAS 嘅 Stephen 井，係呢個香港西九龍站嘅 AP。我哋今次咧好榮幸呢個項目咧獲得香港工程師學會消防分部頒發嘅獎項。獎項對我哋嘅工作嘅認同咧，更加要多謝團隊嘅努力同港鐵嘅支持。大家以專業嘅經驗同良好協調嘅能力咧，打造出一個標誌性嘅高鐵站。喺度再次恭喜港鐵獲獎，同埋多謝學會嘅支持。多謝。
多謝各位，我希望代表 AECOM IDAS JV 用英語致謝。Firstly, thank MTLC for this project. Secondly, thank you for your recognition on our innovation for this iconic and green transportation landmark for a better Hong Kong. You may find the details in newspaper today and include fire compartmentation and smoke zones, static smoke control system for 45-meter tall atrium, virtual smoke barriers for chairside areas, fire protection for the sexy mega columns, smart firefighting lampposts, future-proof paneling, and integrated approach for design, validation, and quality control. Hope all this may help you to deliver a better world. Thank you.
Thank you. In order to raise public awareness of the Fire Engineering Excellence Award and to congratulate all the winners, result was published on Singtel Daily today and on Singtel Daily website. You may check on it. Once again, congratulations to all the winners. Now, let us start the first section and introduce our section chairman, Engineer Professor Eric Lee Wai-Ming, Committee Member of Fire Division. Engineer Professor Eric Lee Wai-Ming is currently a professor in the Department of Architectural and Civil Engineering in City University of Hong Kong. His research area is fire safety engineering, including modeling of fire and smoke development and building evacuation. He has over 120 publications in international journals and conference proceedings. He is also the principal investigator of many government-funded research projects related to fire safety engineering. He is the committee member of the HKIE Fire Division. He has also served as a member of different fire safety-related technical committees in different departments of HKSAR government. I'll pass the time to Engineer Professor Lee. Thank you.
Good afternoon, everyone. I'm Eric Lee, and I'm glad that you come back to the symposium to join this afternoon section. And this afternoon section, we have two parts. In the first part, we have two speakers. After the break, we have another two speakers. So may I introduce the first speaker of this section? He is Mr. Tam Wing Chung. Mr. Tam joined the government as building surveyor in January 1991. He has been working in buildings department for 31 years and is well experienced in building control for both of the new development and existing buildings in Hong Kong. He has been deployed as chief building surveyors of various sections of the buildings department throughout the years. For example, the fire safety section and legal services section, etc. So Mr. Lam is now the Assistant Director of Buildings Department and responsible for various aspects of the corporate service, including the legal services, technical services, minor works and signboard control, research and development, and public education and publicity. So now I would like to hand over the time to Mr. Tam.
Right. Thank you for the introduction. Good afternoon. Engineer Professor Daniel Low, Engineer Professor Chen, Engineer Professor Lee, fellow engineers, ladies and gentlemen. It's my pleasure to share with you the requirements and practices in respect of the control of fire safety performance of private buildings in Hong Kong under the Buildings Ordinance and its subsidiary legislation. Fire safety is always one of the primary concerns of the Buildings Department in planning, design, and construction of buildings. Every fire safety design which should meet the objectives of life safety and property protection and should be provided for protection of life of building occupants, minimization of fire spread between fire compartments and between buildings, prevention of building collapse as a result of fire, and facilitation of firefighting and rescue by fire services personnel. The Buildings Ordinance 1955 is the basis of the current BO. The Building Administration Regulations, the Building Planning Regulations, and the Building Construction Regulations were then enacted in the following year, followed by other subsidiary regulations in a later stage. With respect to the statutory control in fire safety, very limited fire safety requirements were indeed provided before 1955. Although the building planning regulations, the building construction regulations, and their subsequent amendments elaborated more on the requirements on the provisions of fire safety for means of escape, MOE, fire resistant construction, FRC, and means of access for firefighting and rescue, MOA. The requirements laid down in the regulation were not comprehensive. Therefore, the Code of Practice on provision of means of escape in case of fire and allied requirements 1959, the Code of Practice for fire resisting construction 1989, and the Code of Practice on provision of means of access for firefighting and rescue 1989 were then issued to set out technical details for the guidance of building professionals in the design and construction of buildings. The said three codes were the original versions of the Code of Practice issued in relation to fire safety requirements. Compliance with the provision in these codes was deemed to satisfy the respective requirement laid down in the subsidiary regulations of the BO. The BO is subsidiary legislation, and the three Code of Practice have been reviewed and revised from time to time to keep abreast of the developments in building practice and technological advancement. Following a comprehensive review of the Code of Practice for MOE 1996, the Code of Practice for FRC 1996, and the Code of Practice for MOA 2004, a new Code of Practice for fire safety in buildings 2011, the FS Code, was issued to consolidate and replace the three codes. Perhaps coming back to the statutory requirements. One of the main purposes of the BO is to provide for the planning, design, and construction of buildings. Any person who intends to carry out building works is required to appoint an authorized person, AP, a registered structural engineer, RSE, and where necessary, a registered geotechnical engineer, RGE, for the geotechnical elements, to prepare and submit plans for the approval of the building authority, BA. Before commencement of the approved works, consent from the BA is also required. The person is also required to appoint a registered contractor to carry out the building works. No new building shall be occupied unless the BA has issued the occupation permit. Now, for submission of general building plans, superstructure plans, and drainage plans, etc., a curtail check system has been adopted by BD for checking fundamentals issue only. PNAP ADM 19 Appendix A has listed out all such fundamental issues for general building plans, including MOE, MOA, and FRC. MOE. The requirements of MOE are governed by Regulation 41 of the Building Planning Regulations. Actually, paragraph 1 is most important, which says, every building shall be provided with such means of escape in case of emergency as may be required by the intended use of the building. Now, MOA. For MOA, as stipulated under the Building Planning Regulation 41A, B, C, and D, MOA involves 4 parts. The access staircases for firemen, firemen's lifts, firefighting and rescue stairway, and emergency vehicle access, EVA. The first 3 regulations outline the requirements for MOA to allow firemen safe and unobstructed access to all 4 of the building in the event of fire, while EVA is concerning vehicular access and operation of fire engine. FRC. The requirements of FRC are governed by Section 35 of the Building Construction Regulation, which stipulates that a building must be designed and constructed so as to, in case of fire, inhibit the spread of fire, provide adequate resistance to the spread of fire and smoke, maintain the stability of the building, and provide adequate resistance to the spread of fire over the roof of the building to any other building. Now, the FS Code. The FS Code was issued by Building Department in September 2011 to provide guidance on compliance with the requirements of MOE, MOA, and FRC. In addition, it also provides guidelines on the testing standard for the fire properties of building elements and components, fire safety management of buildings, an alternative approach in fire safety design, that is, fire engineering approach. The FS Code comprises 7 parts. Part A shows the framework for fire safety in buildings, the objectives of fire safety and compliance. Parts B to D provide the deemed to comply provisions in relation to MOE, FRC, and MOA respectively. Part E provides the deemed to comply provisions for the fire properties of building elements and components. Part F provides guidelines on managing and maintaining the fire safety provision of buildings to assure that the fire safety provision installed can be operated effectively for the intended life of the building. Part G provides guidelines on fire engineering. Now we come to the principle on use of materials under FS Code. Part E of the FS Code stipulates the relevant parts of the international standard of ISO and the national standards which are considered acceptable to the BA for demonstrating the fire property of building elements and components. As mentioned before, Section 35 of the Building Construction Regulation stipulates that a building must be designed and constructed to inhibit the spread of fire and provide adequate resistance to the spread of fire and smoke. Section 28 and 30 of the Building Construction Regulation also require that the material used for claddings and curtain walls shall be non-combustible. It is stipulated in Part E of the FS Code that different building components and elements like load-bearing and non-load-bearing elements, protection of opening in fire barriers, and non-combustibility, etc., should be tested in accordance to the respective testing standards under subsections E3 to E15 as listed on this slide. As stated in clause E16.1 of the FS Code, the BA recognizes the laboratory accredited by the Hong Kong Accreditation Service, HKIE, under the Hong Kong Laboratory Accreditation Scheme, HOCLAS, or other accredited laboratories with mutual recognition agreements with HOCLAS. The BA also recognizes the certification bodies accredited by the HKIE under the Hong Kong Certification Body Accreditation Scheme, HKCAS, or other accredited certification bodies with multilateral recognition arrangements with HKCAS. As stated in clause E16.2 of the FS Code, the fire properties of materials, products, or construction components shall be tested in accordance with or assessed against the standards stipulated in this part and certified as being capable of achieving such fire property to the satisfaction of the BA. The BA accepts test reports prepared by a recognized laboratory, the BA also accepts an assessment report prepared by a recognized laboratory or certification body. Acceptance of test, assessment report, and certificates of conformity. Under the BO, AP, RSE, RGE, and RC have responsibilities to supervise building works, including the selection and application of building material products, and to certify compliance with the relevant provisions of BO upon completion of works. BA relies on AP, RSE, RGE, and those independent laboratories for testing for compliance with the standards and for certification. PNAP, APP 13, and Practice Note for Registered Contractor, PNRC 25, require submission of tests and assessment reports and certificate of conformity together with the certificate and schedule of building materials and products by the AP and RC upon the application for OP or completion of works. Now we come to product certification system. Product certification is a process in which a third-party certification body, after undertaking the specified procedures, issues a certificate of conformity, COC, also known as product certificate, to a supplier confirming that its product satisfies the requirements of a specified Product Conformity Certificate Scheme, PCCS. PCCS stipulates a set of requirements, rules, and procedures for specific product. A third-party certification body will conduct rigorous evaluation on the product supplier in accordance with the PCCS. For example, by means of factory audit of production or on-site selecting for testing of samples by an independent accredited laboratory, etc. A COC may then be issued to confirm that a product of a given supplier satisfies the requirements set out in the specified PCCS. Product certification can enhance the product quality through upstream control and ensure the consistency in product quality through continuous surveillance of product process in the factory. Initial evaluation for certification of a manufacturer includes factory assessment of production and selection of sample for testing to ensure the continuous compliance with the conditions of certification. Periodic surveillance audit to the plant and compliance tests of randomly selected samples will be carried out. Recertification audit will usually be conducted every 3 years before the expiry of the COC. Thus, product certification should bring benefits to the regulatory authorities as to enhancing building safety due to better quality control of building products. As such, BD issued a new PNAP APP 165 and revised the PNAP APP 13 and PNAP ADM 20 in September 2021, promulgating the acceptance of COC of fire-rated door sets and non-load-bearing fire partition walls under PCCS for passive fire protection products, fire door and non-load-bearing fire partition, issued by accredited certification bodies, as an alternative to the test or assessment reports prepared by accredited laboratories to demonstrate compliance with the BO. In the days ahead, to promote wider adoption, BD is prepared to collaborate with the scheme owners on suitable PCCS to advise on the compliance with the BO so that more PCCS for other building products can be accepted. Central Data Bank. Central Data Bank mainly contains information of building materials, components, and construction systems that have been accepted by BD. Such acceptance in Central Data Bank will generally be based on tests and assessments carried out by the accredited laboratories or the COC issued by relevant accredited certification body. The Central Data Bank aims to provide a reference to the APRSC LGE and other parties concerned in the building industry. It is intended to help sharing of information among the administrators and to enhance public access to information. The test assessment reports and COC should be assessed and certified by the APRSC LGE appointed for a completed private development project as meeting the standards stipulated at the time of submission to BD in accordance with the PNAP, APP 118, and APP 165, respectively. If the APRSC LGE are satisfied with the use of such materials and do not wish to submit a hard copy of the test assessment reports or the COC, which are identical to those listed in the BD list of the Central Data Bank, they may simply quote the reference numbers from the Central Data Bank in their certification. Central Data Bank can be found in BD's website. Last but not least, may I take this opportunity to wish the Fire Division and the institution continued success in the years to come. Thank you.
Okay, I would like to thank Mr. Tam for his presentation, sharing with us the important information related to the control of fire safety performance in Hong Kong. You may have some questions. If you have questions, just type into the Q&A interface. So at the end of all this presentation, we'll have a Q&A section, all right? So now come to the second presentation. That will be conducted by Engineer Professor Asaf Sohail Usmani. All right, so I would like to give a brief introduction to Professor Usmani. So Professor Usmani joined the Hong Kong Polytechnic University in August 2016. He is a professor of structural engineering and computational mechanics at the University of Edinburgh until September 2015. His research in fire safety engineering has focused on understanding the thermomechanical behavior of structures in real fires using computational methods validated with experiments. So Professor Usmani's current research interests include development of computational tools for integrated simulation of structure subjected to fire based on open source software framework OpenSeas. Characterizations of the loading in large pan compartments in the context of performance-based engineering for structural fire resistance. Progressive collapse simulation of tall building under multi-floor fires, and developing AI-based tools for smart firefighting building on the work of the Fire Grid project in UK. This is the current Professor Usmani's primary research focus. So as he's leading an RGC TRS funded 33 million Hong Kong dollar project, Surefire. That is the smart urban resilience and firefighting. Right? So that is the introduction of Professor Usmani. So without further delay, I would like to invite Professor Usmani to give us the talk. Thank you.
Hello, good afternoon, everyone. Thank you, Eric, very much for the kind introduction. I will talk about, as the conference theme is, the webinar theme is about materials, so I thought I'll tell you a little bit about my experiences with working or understanding the behavior of structures made out of steel and concrete, mainly the composite steel frame structures. So we have had a talk before which talked about building regulations regarding fire. So in general, very briefly, the key regulations, the traditional philosophy on how we protect such structures from fire can be expressed in this way. Mainly insulation, integrity, and stability. These three are the key things that we look at. Insulation and integrity typically are provided through compartmentation, maintaining structural and thermal barriers to prevent spread of a sufficient length, prevent spread for a sufficient length of time to enable safe exit of all occupants. Stability is focused on structural members, and it involves fire resistance, the quality of or the property of fire resistance, the length of time a structural component withstands exposure to a standard fire while retaining adequate capacity to resist fire limit state load. So this is typically the standard approach, traditional approach. So if we observe, say, this approach on concrete and steel composite building, which is usually some sort of a composite, involves, having on the right-hand side, you can see top right-hand corner, you can see a steel concrete beam subjected to fire, or you could see this is a floor system with a steel supported floor slab, and if you heat it, what we observe is that the fire heats the steel rapidly. And the steel loses stiffness and strength at temperatures above 400 degrees C. And the bottom left graph shows you that the strength of steel is about half of what it is when it reaches 550 degrees C, half of the ambient strength. And so that is typically seen as a limit that we must keep. Concrete also loses strength and stiffness, as the graph on the bottom left shows. But in case of concrete, typically, because concrete has, compared to steel, much lower thermal conductivity, so concrete actually doesn't lose so much of its sectional strength and stiffness, because most of the heat is limited to the surface layers. Okay, so if you have a thick enough, so typically that's the general understanding of material behavior in fire. Okay, so based on that understanding, the traditional proposed solution is protect all steel for a long enough period because of its properties, but provide sufficient cover to reinforcing bars in typically, because concrete is typically not just concrete, you have steel inside it, reinforcing bars. So we provide cover to reinforcing bars for a sufficient depth, so that they are protected from the heat effects. Okay, and then we apply a standard fire curve, typically, traditionally, which is a 100-year-old curve that was developed in the USA. And they've got many versions, like British Standards version and other. And so we then decide on the basis of this as to how long we are going to protect. We are going to protect the structural member. So this is the traditional approach, prescriptive fire protection approach. And this is a book by the yellow book used to be called, that was used in Arab for designing structures in fire. So it's basically, the principle is that if you have, because you want to protect steel, so typically when the steel is like on the top right corner, you see a thicker beam. So the surface area is lower and the volume is higher, But on the left side, left top side, you see a beam where the surface area is higher and the volume is relatively lower. So this the left beam will typically in a fire heat much faster, and the right beam will heat slower because of larger volume and lower surface area, because the heat has to enter through the surface, right? So typically you can adjust the protection based on this section factor, the surface area over volume ratio. Okay, and then you have different requirements based on local regulations. So this is like the requirement in England and Wales for different types of construction, residential, offices, commercial, storage. So that gives you the number of minutes, and based on height, you need number of minutes you need to keep the protection. So that was the on the standard fire curve. Yeah, and then based on the you can go into tables and look at the surface area volume ratio, and then look at the requirement from the code of how many hours you want the protection for, if it's half an hour, 1 hour, or more, and then you can get the dry thickness in millimeter for the insulation thickness that you need to apply to achieve that protection. And this is the kind of insulation thickness you get. You know, this is the different options you have, like board and spray and intumescent paints and blanket. All of these are just shown. So this is basically what generally happens, and it's been happening for a long time in this way. The consequences of what we of this way of thinking about fire safety and fire resistance of materials and structures is that reinforced concrete structures are considered to be more resistant, considered to possess inherent resistance to fire, while steel frame structures are considered to require protection against fire. So this is what people think. But then when you look at reality, you see the concrete structures also fail in fire. So this is a picture that you know is from Switzerland, Gretchenbach. It happened in November 2004. This is an underground parking garage where a flat slab construction of concrete. So there's no steel there, it's all concrete. You can see the columns poking out of the grass. These are essentially, this is a punching shear failure that happened in fire, and 7 firefighters were killed in this. So concrete structures fail. This is a Delft University in Holland, architecture faculty building, May 2008. Part of that building collapsed in a fire started in a coffee maker or something. Okay, so basically these concrete buildings also suffer significant failure. Based on our understanding, shouldn't happen, right? So the idea is that our understanding is probably faulty. So and of course the steel industry doesn't like it so much because the fire protection part adds to the significant cost, and it can be the cost of fire protection can be 10% to 30% of the cost of the structure, based on height, usage, etc. Okay, so there have been sort of major events like Broadgate fire, June 90 in UK, where the steel members were not because the building was still under construction. The steel members were not protected, and the fire lasted for 4.5 hours with high temperatures. But typically, the building did not suffer too much, despite the steel members not being protected. The total losses were around £25 million, but the structural repair cost was only 2 million, and they were completed in 30 days. So it shows that, you know, the expectations, the reality may be different from our expectations in terms of what material behavior is. So I'll tell you why maybe this is the situation, because what we assume is isolated structural members. When we look at the behavior of steel, beams, etc., then we look at isolated structural members in a furnace, because we base it on the entirely the material behavior. But the reality is that the structure is like a composite beam like that, and it behaves in an integrated manner, and the structural response depends upon much more complex situation, and the real fire also is not a standard fire. This is a typical compartment fire curve, and this is a kind of representation of a compartment fire. You can have ventilation controlled, or you can have fuel controlled fires. If you have a fully developed fire, then this is a famous graph which shows that the ventilation controlled fire typically maybe can be a little bit more severe than the fuel controlled one. So basically what we say that if you have natural fires, unlike the standard fire, then you can have different fires based on the ventilation conditions and the fuel load, and you can have fires which are maybe hot and short-lived, and you can have fires which are relatively cooler and longer lived. Okay, quite different from the standard fire. So in that case, the time aspect of the standard fire doesn't make much sense. So if we then apply this different fires to basic structural mechanics, so this is an example of a restrained beam. Typically this restrained beam is a good representation of a realistic structure, because structure beams are not isolated, they are connected to other parts of the structure. So you can assume that these boundaries are springs. And then when you heat this beam and assume that this is a composite beam with a steel and concrete, as I've mentioned, and the temperature distribution along the height is as shown on the left-hand side graph, that the concrete at the top is going to be very cool, concrete exposed to fire is going to be hotter, the steel is going to be the hottest. Yeah, so that's the temperature distribution. So what we do is, this temperature distribution is so complicated, then we say that this temperature distribution is equivalent to some uniform temperature increase delta T and some thermal gradient T comma Y. We can decompose that, right? We can do some decomposition, and then we apply that separately to understand what it does to a beam. So let's start with a simple beam. This is a simply supported beam with the left, you can see the left support has rollers in it. So if you heat the beam with a temperature delta T, what you'd expect, it will just expand. Yeah, whether it's made out of concrete or steel doesn't matter, both expand in fire. Okay, so it just moves a little bit towards the right. Okay, and we can calculate that. It's very easy to calculate if you know the thermal expansion coefficient of the material. Okay, now if you remember, it was not just the uniform temperature increase delta T that we are talking about, we're also talking about the thermal gradient. So if we apply a thermal gradient to the beam, no mean temperature, just a thermal gradient, then the reverse happens. You see the roller moves to the left this time. Yeah, it's a uniform, because there's no expansion, it just curls because of the temperature, thermal gradient now. Yeah, and we can also calculate that. Yeah, but obviously these things don't happen separately, they happen together. So what may happen is that both one moves right, one moves left, so you can see that those are cancelling motions. So you may actually have significant deflection, but actually not much stress in the beam. Okay, so it just the fire just curls the beam. But when firefighters or engineers who are not trained look at the high deflections, they think that that's because it's weak and there's too much loading. That's why it's deflecting. But it's just the thermal deformations. Okay, so this is just further looking at the same thing, whether if you're restraining the beam instead of now having rollers, then if you apply delta T, then you get a compression force in the beam. If you apply the gradient, you get a tension force. If you fix it from rotation, the bottom figure, then you get a moment. So basically what it means is that in a restrained situation, because typical in a beam, buildings are not rollers, they're connected on both ends and they're restrained to some extent, then depending on the restraint, depending upon how much mean temperature or gradient you apply, you get very, very different behavior. Yeah, and this is what it shows. So this is what so we can take a little model of this 9-meter length beam and apply a uniform temperature delta T of 400 to all cases and look at 5 cases of applying different gradients. So first is 0 gradient, and then the last is 10 gradient of 10, and then increasing up to 10, 1, 3, 5, 10, right? And this is the deflections you get. The top one is basically, you see no deflection because there's no gradient. Okay, so what happens is the beam just keeps having compression forces, and at some point it buckles. Yeah, if you take a column and you press it, you take a stick and you keep pressing it vertically, at some point it will just get out of the way. Yeah, it will buckle. So that's a buckling deflection. The other ones are gradient based, and those are larger deflections. Okay, so anyway, and this is the axial force, which shows the bottom one now is the 0 gradient, where you see it goes up to a value, and then when it comes to the buckling load, then it stays constant, right? But when you look at the top one is the highest gradient. The bottom ones are all compression forces. The top one, it goes into tension because it's a restrained force. Okay, because it's restrained, ends are restrained. Okay, so what it says is that when you apply the realistic fires, then you can have very different behaviors of this beam. Okay, and different failure mechanics and different mechanical responses are produced. Okay, so we can make some solutions like this. I won't go into that. And this is then seen in real structures. So this is Cardington test that we were involved in the mid-90s in modeling this through a research grant. And in this, we can see that this is one of the tests of a beam. You can see the discolored area. That's where the fire was. Okay, and we made a model, and we looked at the results of the model. The model shows that the deflection and the bottom flange temperature is just a straight line, but if you change the thermal expansion coefficients of steel and concrete, then you get completely different figures. So I won't go through that because it gets a bit complicated. But what you see is at very low temperature, you see the beam bottom flange is buckling. Okay, there you see, and because it's the restraint is too high, the rotation restraint, and the top of the slab is also cracked. Okay, so you get a bottom flange buckle at top of it because it's trying to bend, but it's not able to bend, so it's cracking at the top and buckling at the bottom. Okay, so you see then, and when it cools down, then it becomes shorter because there are plastic strains in it, so it pulls off the connections. Okay, so this is what we sort of basically learned that these are the basic mechanics, and we applied it to an Arab project where we did the analysis of these areas and applied a short hot fire and a long cool fire, and this is the two areas that we modeled. But these panels are interesting. So you see, let me see if I can get the video going. Is the video? Yeah, it goes. Yeah. See, so if you apply the fire to this part of that building, you can see the column being pulled by the sagging slab, which looks dangerous. So what we decided that we said that the protection should be applied to all the beams that are connected to columns, and then if you look at the deflection, then you get a much better behavior, and the column is not pulled anymore. So we asked them to then, so this is like a performance-based engineering, fire engineering approach, where we then, you see the beams that are shaded are protected, and the beams that are not shaded are not protected, are left, and they saved a lot of money on that, about 250K on 250,000 pounds on this, on fire protection. So we looked at, then the World Trade Center collapse happened, and we started modeling that. And so this is showing us that this similar behavior that we saw in the consulting project, we see that the Twin Towers could have collapsed in this way, that the fire sags the floors and the floors pull the columns in. You can see this here even more clearly. You see? Yeah, that basically is what we feel is the mechanism of tall building collapse, which is completely ignored in design, because we are so material focused. So in a sense, I'm talking about materials, but I'm saying sometimes that materials and structures are both important, and material behavior is obviously important, but we should also look at the structural behavior. And so we look at the pictures, and you can see some pictures which are showing those kind of inner sags, yeah, inward bowing. This is not my saying. It says NIST report, which is saying the inward bowing of perimeter columns of 2 minutes before collapse. So you see that. So I'll skip that because I'm running a bit late. Basically now, this is just, you saw that picture before, this concrete steel composite. This is the material aspects as well. So I'm trying to see what is the full range of behavior that we see in these composite actions, you know. So the left is rigid restraint situation, but this is not realistic, because beams, typically you have columns and the beam. And if you then have, so depending on the stiffness of the flexural stiffness of the column and the flexural stiffness of the beam, you get different levels of restraint. Yeah. So if you don't have, if you have infinite restraint, you get this behavior. You saw those pictures. So now these are basically showing the axial forces and deflections of the beam under different temperatures, 200 to about 500. Okay, this is the case of the finite restraint, not infinite restraint, where the column is where you see the column on the left-hand side, and here again we apply different gradients, 0 to 10 degree C per millimeter, and we use different stiffnesses of the column, 1, 4, 10. So the 4 figures are different stiffnesses. So the first one is the same flexural stiffness as the beam. The last one is 100 times, which is almost fully restrained, and 4 and 10 are more realistic. So you see that you still get your tension forces and compression forces depending on different gradients. Okay, so you get different behaviors. Again, this is deflections for the same case. Now, if we want to see whether those situations happen in real beams, then this is some analysis we did where we looked at 60 universal beam sections and applied them to 1 hour standard fire exposure and looked at the actual gradients that happen. And you can see that we used from 0 to 10, so you see the whole 0 to 10 range appearing. So especially when you have sections which are, you know, the bottom is section factor. Section factor, if it's high, that means the perimeter is large, volume is low, so more like thin. So if you have modern buildings, the modern buildings typically are long span. In long span, they have kind of deep beams, cellular beams, etc., and relatively thin slabs. So they kind of correspond to this high section factor situation. So there you get very large gradients. That's what basically this is showing. And this kind of a situation. Yeah. So gradients are very strong. but these are not considered in our design at the moment, because our design is only about protecting the steel from fire. Okay, so this is just a whole range of different times of the same, because that was which is a difficult graph to explain. But yeah, I'm finished almost. Okay, so this is just showing the range of gradients in real composite sections at 5-minute intervals up to 60 minutes. And the bottom is range of mean temperature in composite sections at 5 minutes up to 60 minutes. This is just the whole, from top to bottom, you see 5 rows. 5 rows are 5 different slab thicknesses. Okay, and the top one is about thermal gradient range, and the bottom is the mean temperature range that you find in real. This is a heat transfer analysis of 60 sections over a period of 60 minutes. Okay, so the first one is after 5 minutes, and the last one on the left, and after the end one is about 60 minutes. Yeah, and when it's 60 minutes, first one is, yeah. So that's the whole range of time, the gradient and mean temperature distribution. You can see in the bottom figure, the top row of the bottom figure, you can see the mean temperature increasing over time. Yeah, you see. So I think this is you can see those effects. Basically, it's saying that the gradient is still quite high for high section factors. Okay, but these figures we have recently produced this, so we are still analyzing them, but they give us an understanding of what is the real situation in terms of because the key parameters that I've discussed today that influence structural response are the mean temperature that you have in a structural section and the thermal gradient. Okay, and those these are just more sort of detailed examination of those. Okay, so I think that's probably all I have to say. Yeah, thank you.
Okay.
Thank you, Professor Osmani. Ladies and gentlemen, let's take a 15-minute break now. After the break, we will have 2 more presentations followed by our Q&A session. Don't miss the chance to submit your questions anytime during the presentation. Thank you. Welcome back, everyone. Let's start our final session. May I now invite our session chairman, Engineer Professor Lee, again to introduce our speakers. Engineer Professor Lee, please.
Hello, everyone. This is Eric Lee from CTU again, and we'll start our second part of the afternoon section. In this second part, we also have two speakers. So I would like to introduce the first speaker, Engineer Professor Richard Yuen. So Engineer Professor Richard Yuen is currently the Chief of Staff, Vice President, and Chair Professor of Architectural Engineering, Civil and Architectural Engineering of the Department of Architecture and Civil Engineering in City University of Hong Kong. He was the head of Department of Architecture and Civil Engineering in 2018 to 2019, and the acting director of Communications and Public Relations Office in 2019, City University of Hong Kong. So Engineer Professor Yuen research interests include fire safety and engineering, pyrolysis and combustion, applications of computational fluid dynamics, that is CFD, fire retarding materials, neural network modeling applications in fire engineering, HVAC and control engineering. So Engineer Professor Yuen is a registered professional engineer, members of the Institute of Fire Engineer, IFE UK, Society of Fire Protection Engineers, that is the SFPE in USA, and a fellow of Hong Kong Institution of Engineer, that is Hong Kong IE. He has been engaged in research consultancy and industries and served actively in professional institutions. He is also the founding member of the Disciplinary Advisory Panel of Fire Discipline of Hong Kong IE. Currently, Engineer Professor Yuen is the council member and deputy chairman of Quality Assurance Committee of the Hong Kong Council for Accreditation and Academic and Vocational Qualification, and the members of Fire Services Training Advisory Committee. So I would like you to join me to welcome Professor Yuen to deliver the talk to us. Thank you.
Thank you, Chairman, Professor Engineer Eric Lee. Good afternoon, colleagues, ladies and gentlemen. My name is Richard Yuen, and I'm currently the Chief of Staff and Chair Professor of the Department of Architecture and Civil Engineering at City University of Hong Kong. Today, I'm very honored to be invited by the Organizing Committee of the Hong Kong IE Fire Division Annual Symposium 2022 to give a talk entitled A Novel Multi-Scale Approach for Study of Performances of Flames Retardant and its Application for Building Facades. This work has been co-authored by my colleagues in University of New South Wales, Professor Guang Heng Yo, who gave a speech this morning, and also Dr. Anthony Chen Yin Yun from University of New South Wales, Australia. Now, to start with, I would like to give you a very quick background of what we are proposing. Now, as we all know, the devastating nature of fire creates disasters that will result in a great loss of both life and assets. By post-fire investigation reports, it is notable that these fires were caused by extensive use of composite material in building products, as highlighted by severe fire incidents such as Grenfell Tower fire in UK. Nowadays, because of a rapid change to building and developments in architectural technology, it has been led to more complex structure which use a stronger and more lightweight component. Composite materials are known to be a good candidate because of their lightweight and cost effectiveness, as well as their flexibility in manufacturing. However, a major disadvantage of this composite material is their poor fire performance. When they are exposed to a high temperature, these composites will break down to release volatile combustibles. When react with oxygen, will generate heat, namely the fire, as well as a number of gases including carbon monoxide, hydrochloric acid, and also hydrogen cyanide, which are toxic and responsible for the death and injuries in most of the building fires. That's why we need to study the fire development involving those composites, whether it is fire retardant or without fire retardant. Now, fire by itself is a very complicated phenomenon involving chemistry and physical processes which are highly coupled and highly nonlinear. Now, these processes include combustion, soot formation, fuel air, turbulence mixing, heat exchanges, etc. Experimental investigation can provide good quality information of the fire phenomenon. However, they are usually very time-consuming and costly, as well as destructive. Although reduced scale or bench-type tests may provide useful data, the extrapolation of such results from experiment to large-scale fire analysis often present very large discrepancy due to the dynamic and geometrical effects which may not be scalable. Computational fluid dynamics, on the other hand, known as CFD, or fire field model, have become widely adopted in fire phenomenon analysis and prediction, owing to its intrinsic scalable capability, taking into account fully fire dynamics and geometrical factors, and other essential elements such as reaction of a wide range of combustible fuel type, etc. Now, the computational approach, as I mentioned, can be adopted, as I said, for fire retardant material behaviors to address particularly the reduction of combustibility of external claddings by providing fundamental understanding of the burning characteristics of those materials. And in order to have an effective CFD prediction, we can understand the fire for its key issues, which is important, especially for fire retardant polymers. Okay, and while the full-scale fire experiments may be conducted to replace the actual fire scenario for the assessment of fire behavior and performance, yet they are very costly, as I mentioned, complicated, and produce large amount of pollutants. Modeling is a way to become an alternative. Now, development of a robust numerical model to address the needs of fire safety assessment of fire-resistant polymers will be highly beneficial to the current fire safety community. For just the solid decomposition, or what we call pyrolysis modeling, there are a number of challenges that we have to overcome before we can use the modeling techniques in our CFD calculation effectively. These challenges include the following: regression of the solid region and variation in porosity and material properties, radiation, convection, and conduction heat transfer between gas and solid phases, conduction heat transfer within the depth of the solid region, initiating pyrolysis and char reactions, emission of gas phase fields and couples with the combustion process, and also what is very important is the detailed chemical kinetics involved during the combustion and soot formation processes. In the traditional way of characterization of materials flammability, we employ very conventional bench-type tests such as thermogravimetric analysis, we call TGA, and or cone calorimetry. They are very useful in characterization of material flammability and properties. Now, in this talk, while I propose a multi-scale approach, I would stay with the conventional bench-type TGA experiment rather than what has been covered by Professor Guang Yu this morning, using molecular dynamics as a more advanced tool to satisfy this multi-scale approach. So I will restrict myself to experimental discussions. Now, here is a flowchart that demonstrates the process of how we can study material flammability characteristics. Firstly, we can perform TGA analysis to study the thermal degradation process, and we can characterize pyrolysis kinetics, which will be further applied to run the pyrolysis model, or in fact we can extend it to CFD calculations. Meanwhile, cone press, the FTIR tests can also be carried out to study material fundamental burning behavior and gases emissions. After finishing all experimental tests, finalized kinetics can be used to run the pyrolysis model numerically or the CFD for the 5 predictions. And at the end of this talk, I would also compare those calculations with the experimental observations to make sure that they are valid. Now, first of all, let me go through a method of pyrolysis kinetic characterization. Now, this is based on the mathematical expression called Arrhenius expression, where the reaction rate dx over dt is given by 2 terms. The first term is a temperature-dependent term, and the second one is a conversion-dependent term. And if you look at the temperature conversion, temperature dependent term, the Arrhenius expressions give bracket t equal to the pre-exponential function, pre-exponential factor A times the exponent of bracket activation energy over R, which is a gas constant, and absolute temperature T with a minus sign. And with this expression, we can go one step further to take a log of this expression, which will result in a linear relationship between the left-hand side and the right-hand side parameters. Now, this approach has been proposed firstly by Kissinger, Akihara, and Sunos. We call KAS approach. Now, this is a very conventional approach that will help us to generate or identify the pyrolysis kinetics for various components of a composite material. Now, if you look at the result, the graph on the right-hand side, you will see that this is a typical result of a composite material being undergoing thermal TGA experiment analysis. And you can see that the experimental curve resulted in a number of peaks, roughly 3 peaks. Namely, therefore, there should be 3 parallel or sequential pyrolysis reaction going on in this composite material. With the KS model, each of this peak can be used to identify a set of the A and E value, that is the exponential factor, and also the activation energy valued as a couple for each of them. And then, in order to optimize and get the best fitted values for A and E, a generic algorithm will be applied. to do parameterization or optimization, and using this GA approach, we can optimize the pyrolysis kinetics from the KS method. And then finally, we can use the optimized parameters to mimic the pyrolysis kinetic result which we obtain from the TGA analysis for various temperatures, such as 5 degree K time steps, or 10 degree, or which is too small, 20 degree. Now, in fact, if we take a typical TGA curve of a certain material, here is the high density polyurethane, we can identify two peaks as shown on the left hand lower corner of this slide, and we can identify two reactions, R1 and R2, with respectively E1 and A1, E2 and A2, shown in the table. And when we put this optimized kinetic value back to the our pyrolysis model, we can basically regenerate the TGA curve and compare with experiment with good agreements. And therefore, the way that we can we obtain the pyrolysis kinetics is a very effective and useful data for further analysis of the pyrolysis of those composite material when different fire scenarios occurs. So we can apply this to a number of material by just repeating the whole process. And finally, I would like to present to you a couple of validation by using the fire tests. Firstly, by a bench type tests at a bench scale. Cone calorimeter has been a very useful equipment, bench type equipment to explore the burning characteristics of composite materials. Here are some of the samples before and after burning in the cone calorimeter. And because of the timing, I would like to go very quickly. A cone calorimeter consists of a radiation heater where the sample is placed on the sample holder, and the dimension is standardized so that when we excite the material by the radiation heater, the material can be ignited by a spark, and there we can measure the heat release rate as well as the gases emission from the burning material. Now, the result of this cone calorimeter tests can be divided into a number of observations. For example, we can obtain gases emission like carbon monoxide, HCN, etc. And then for different material, we can do the same test and obtain those values one by one. Now, and in order to demonstrate the multi-scale approach, we propose also the CFD calculation by using numerical modeling, repeating the cone calorimeter experiment. Now, without going into details, I would like to show you some of the results that we obtained for the low-density polyurethane foam. On the right-hand side, this is a numerical result with the animation of the flame that is being generated and predicted by the CFD calculation. Now, in this calculation, we use FDS as the which is a well-known software developed by LIS for fire calculation. The only thing that we make use of from the previous discussion is the chemical kinetics, the pyrolysis kinetics that we obtain from the KAS analysis based on the TGA experimental result. So from the TGA, which is a bench scale, experiment involving a very small sample. We then extend it to a larger scale sample, such as this, in this case, the 10 centimeter times 10 centimeter composite material being experimented and tested under a cone calorimeter. Now, if we take a closer look of the prediction, we can compare the heat release rate of different materials resulted from the experiment as well as the CFD calculation using FDS based on the kinetics we obtained from various experiments. And we can see that it is a very, very good fit in terms of the prediction, which is a blue line, which is a dotted line compared with the blue line, which is from the experiment. Now, how about facade simulations? For facade, we can also perform experiments. According to our study, we use the British standard tests for various facade material, and then these are full-scale tests. And we can use the kinetics that we obtain from the bench scale approach, and then put into our FDS simulation. We can obtain the simulation predicted flame spread or fire behavior as shown on the left-hand side of this slide. You can clearly see that the photos depicts the development of the fire over the burning facade from 1 minute to 9 minutes. And along with it, there are CFD calculated result prediction that is comparing extremely well, even down to the spread between panels. If you look at the slide very carefully, you can see that there is a lower panel and an upper panel. And the flame actually in the experiment spread around 6 minutes from the lower to the upper panel for this facade without flame retardant. And having got very good agreement, we can confirm that this multi-scale approach is very useful, and therefore we move on to the right-hand side to look at the facade material with the flame retardant. And we can see that although we do not have yet the experimental result, but you can see that from the result, the spread from lower panel to the upper panel literally is 9 minutes instead of 6 minutes, because this is a flame retardant material. So effectively we can capture the characteristic of flame retardant using kinetics that we obtain from a separate bench type experiment, and then input and inform our CFD calculation to do a very effective calculation, even for flame retardant materials. So our preliminary observations confirm that this multi-scale approach can help us to perform holistic analysis of flame retardant material or material without flame retardant for bench type fire tests as well as the full-scale tests. And because of the time limitation, am I running out of time?
Is it? It's okay, I think.
It's okay.
Yeah.
Okay, so I can flip through a number of slides.
Mm-hmm.
Now, potentially, we have the opportunity now to study more full-scale fire, like building facade fire. And as you can see that over the years, we have a number of disastrous fire over the buildings due to the facade material combustion. And it is very promising if we rely on this multi-scale approach. Firstly, obtain the right kinetics of the composite material. Secondly, we apply the kinetics to the pyrolysis model. And finally, we can combine this pyrolysis model with the CFD calculation to predict or to investigate fire scenarios involving full-scale fire facade fires, building facade fires, as well as the prediction of performance of building facade if we have some new material being invented. And finally, I would like to give you some of the potential prediction that we can obtain. Of course, I have not got this result yet because it's, even computationally this is very costly. Not to mention that it is impossible to do fire tests in such a scale because it will be very disastrous. And then these are some of the possible simulation results over facade with composite materials. And I would like to end my presentation with some acknowledgement to the funding agency. This work has been fully supported by Research Grant Council of the Hong Kong Special Administrative Region under the project CityU 1121-4221. And also I acknowledge my greatest thanks to the co-authors at the ARC Training Center for Fire Retardant Material and Safety Technologies, namely Professor Yeo and Dr. Anthony Yuen. And with that, I would like to pause here. Thank you very much.
Okay, thank you so much. I would like to thank Professor Richard Yuen for his presentation, which shared with us the latest frontier technology related to the application of multi-scale approach for the studying of performance of fire retardants. All right, so you may have some questions. So please feel free to type your question in the Q&A box, right? So at the end of the next presentation, we'll have the Q&A section. Then we will discuss all these questions together. And now that's the time for the second presentation. It should be the last presentation of today. That would be the presentation to be conducted by Professor Wang Yong Chang. So Professor Yong Wang is Professor of Structural and Fire Engineering at the University of Manchester. He's a famous international leader in research on all aspects of fire resistance of structure, including supervision of a number of research projects on thermal properties of fire protection materials, the results of which will be summarized in his presentation at this symposium. He is the only UK representative in all phases of the European Union project for the revision of Eurocode for fire resistance design of steel and composite structure. He was associate editor of the ASCE Journal of Structural Engineering and responsible for fire resistance, and he is currently a member of engineering panel for UK's 2021 Research Excellence Framework, that is REF. He is the director of the University of Manchester's UKCRIC, that is the UK Collaboratorium for Research on Infrastructure and Cities, National Laboratory for Infrastructure Material under extreme loading conditions. So again, without further delay, I would like to invite Professor Yong Wang to give the presentation. Thank you.
Good afternoon. I'm sorry I can't be with you in person, but I'm hoping my short presentation will be of some use to you. My name is Yong Wang. I'm from the University of Manchester, and today I would like to say a few words about thermal properties of fire protection materials. I will start by explaining why it is so important to have accurate information and data about thermal properties of fire protection materials. I will then report to you about some of our current studies and progress so far, focusing on intramural coatings, gypsum, and other generic fire engineering materials. But as I'm sure you will know, there are still many challenges in understanding the thermal properties of fire protection materials. So I will then point to you in a few directions of future research. Let's then look at the general situation of quantifying structural fire resistance. I'm pretty sure you all know that there are three general steps of quantifying structural fire resistance. In the first step, we try to understand, well, we specify the design fire scenario, so-called fire dynamics. Even though there are still quite a bit of research studies going on in understanding fire dynamics, I think there is now good agreement in the design fire scenarios. Then we carry out heat transfer analysis to obtain temperatures in structures. In this case, then we need to have input data, thermal properties of structural materials, as well as thermal properties of fire protection materials. In terms of method of heat transfer analysis, it is very mature, well established. And also in terms of thermal properties of structural materials, there are good enough information for doing so. But it is the thermal properties of fire protection materials which are problems with us. In terms of structure analysis, again, the methods are quite difficult, takes time to do, but the methodology is quite mature as well. And of course, then we need mechanical properties of structural materials for doing structure analysis. Again, there is good enough information. So it is then thermal properties which are then troublesome. Let's then look at the situation we have so far. In terms of thermal properties, you may have come across such information which then gives you so-called generic information of thermal properties of various materials. Thermal properties being density, thermal conductivity, specific heat, and in some cases maybe some moisture of materials. So what we have in here is then so-called ambient temperature properties. The manufacturers might then provide you with such information because they need to have the information to allow you to, for example, carry out energy consumption at ambient temperature. At elevated temperatures, it might be possible to follow this standard in here to quantify the temperature-dependent thermal properties of fire protection materials to structural members. And many of you might be already familiar with the Eurocode 3 equation for calculating the temperature of protective steel. This method of calculating the thermal properties, temperature-dependent thermal properties of fire protection materials is no more than an inverse method of analysis for material properties. It is really the inverse solution given you know the temperature of the fire as well as the temperature of the steel from a fire test. You then work out reverse direction to work out the thermal property of the fire protection material. So this then is the method which is in the Eurocode for calculating the temperature of protective steel, and this is then the inverse calculation method. But of course, this method is quite difficult. There's a lot of problems. So, for example, it requires a lot of expensive, large-scale fire testing, so it is very expensive and time-consuming. It is also then not good enough because it lacks general applicability, because this method has no understanding of the fundamental sciences which affect thermal properties of materials. And it can't really then distinguish between different effects which then might affect thermal properties of materials. Because of this, then it is very difficult to apply this method across the board. So even if you're then dealing with normally the same material, you may get different results because they have different various effects. So that's the first problem. The second problem is then that it is based on this lumped mass assumption for calculating steel temperatures. So what we're getting then from this method is an average value of thermal properties. And of course then this then makes it not suitable if you're doing more refined numerical modeling of temperatures because you want to look into non-uniform temperature effects. And of course then also it can be a round model because not all materials have their thermal properties which are temperature dependent, especially with intrametallic coatings, as I will explain to you. And intrametallic coatings just happen to be for now, the most common way of protecting steel structures. So how bad could the situation be? So what I have done in here is then I've used the temperature calculation equation in the Eurocode for protected steel. One, assuming then that the material thermal properties are constant at ambient temperature. And the other one, then I change the thermal properties of material, especially the thermal conductivity of the material, as a function of time. So you can say in here, this piece of steel has now totally different temperature time response without changing thermal properties to be temperature dependent. After 60 minutes, I get about 200 degrees. But if I then include temperature dependent thermal conductivity of the material, I then get 600 degrees. Totally different results. But we don't really need such big difference to cause big problems in our calculations. So what I'm showing here is then the variation of strength and stiffness reduction factors of steel as a function of temperature. Many of you are familiar with this already because you are all from the Steel Institute of Hong Kong. If you then look into this in here, let's then look at the yield strength of material. In the region of temperature of interest, which is around from about 400 degrees to about, say, 700 degrees. A small change, say 20% in temperature, can cause a huge change in the yield strength of the material, that's 40%. So as structure engineers, we struggle to get things within 10 or 20%, but if you then make a small mistake in temperatures, then whatever we do to improve the accuracy of our structural calculations may be just then in vain, because we can't really achieve that. So it really then is important to have much better accuracy, control of accuracy of calculating the temperatures of steel. And that, of course, then depends on thermal conductivity or thermal properties of the material. So what is the situation now? I'm just going to use then some of our research studies to inform you the progresses which we've made so far. But as I say, there will still be a lot of challenges. So first, I will deal with intrametallic coatings. Of course, intrametallic coatings nowadays are the most frequently used fire protection materials, certainly in the UK. So this is then a tubular steel with concrete fill inside. The white color in here is intrametallic coating. In this case, in here, the concrete filled tube is unprotected from this level down. Intrametallic coating protects steel by expanding after being heated up. That is then its main function or the main mechanism of providing protection. Because it is by expansion of the coating, then it's important to understand the expansion mechanism. And the expansion mechanism is not just then temperature dependent, it's also then dependent on the rate of heating. That's really important. So what we have done in here then, we've done some fire tests and we've plotted the temperature time curve, the thermal conductivity temperature relationship based on the inverse calculation which I mentioned earlier on for the intrametallic coating which we've tested. As you can see in this region, which is of course the most interesting, most effective region of fire protection, the thermal conductivity of intrametallic coating varies hugely by almost orders of magnitude. And that's really important. We can't simply then use some sort of average temperature, thermal conductivity temperature relationship. We really have to understand the expansion mechanism. And that has been what we've been doing for some time. How does expansion occur? Well, if you've got a substance which has some gas inside, and then if the pressure of the gas is increased, then of course then it expands to be such a size. That is really the mechanism. And many years ago, a very clever scientist then did actually do some research and then derived an analytical solution to say how much expansion changes as a function of time, as a function of the pressure of the gas, as well as its surface tension of the bubbles inside. So we then adopted this theory in our calculations. Well, of course then, to do that, we need to calculate the pressure, but of course pressure then simply comes from the decomposition of solid intramesinal coating into gas, because solid intramesinal coating is about 1,000 times denser than gas. So with that, then we can calculate the pressure. And of course then, it is possible to measure the surface tension and the viscosity of the material. So that is what we've done, and then we have then implemented this in our research. And of course, in order to, of course, expansion stops at some time, and then when it stops, some bubbles are produced, and of course we need to know the bubble size in order to then relate to thermal conductivity of the material. And we have found 3 millimeter is about the final average bubble size. So with these assumptions, then we have then predicted the thermal expansion or the expansion of intramesinal coatings as a function of temperature, and these are our results under different heating rates. This is so-called cone calorimeter heating. So we then predict expansion ratio as a function of time under this heating rate for different thickness of steel and the coating. And you can see in here the results are quite good. So that's our the test. These are predictions. There is, of course, this stage of reduction in expansion that's caused by oxidation, which can be relatively easily dealt with. So that is then under this heating, that's done under different heating level. Again, the results are quite good. And if you're interested, then we have published a couple of papers. One is then about the expansion process, and then one, of course, then to convert from expansion to thermal conductivity on intramesinal coatings. So that's then on intramesinal coatings. Another piece of research which we've done on intramesinal coatings is then look at the variabilities. As I said, we have adopted a theoretical solution for an idealized situation. Of course, then real life then is not idealized, so there are variabilities. There's also then another source of variability, that is the thickness of intramesinal coatings, the so-called dry film thickness. So if, for example, we say the dry film thickness is 0.4 millimeter, in fact, that can be a range of values that you would get in real life, as in other coating thicknesses. So putting things together, we then have carried out a probabilistic modeling of structure behavior with these variabilities, and to then have then derived a number of safety factors, depending, of course, on sort of failure probability. Again, you can then find our results in this paper. So that's then on intramesinal coating. Another aspect of intramesinal coating, of course, then is degradation over time. Intramesinal coatings are chemical materials. They are reactive chemical materials. When they're exposed to the environment, they can degrade. And then that then causes the function of intramesinal coating to lose. So, for example, this is our fresh intramesinal coating. Once after heating, then we can expand to something like 9 centimeter, and this is simulating, say, for example, something like 10 years of exposure, and afterwards you can then barely reach about 2.5 centimeter, and after 20 years of simulated exposure, it's almost nothing in there. Now, in this case in here, we have not applied any top coat. Of course, in reality, you do have top coat, but then even with top coat, you don't then eliminate this problem. And of course, with top coat, you have other issues as well, like cracking. So then we have then carried out quite a lot of research to study these effects. Again, if you're interested, we have publications to help you understand some of the problems in here, as well as, of course, hopefully then our research results. So that's then the first aspect, material. The other material then is gypsum. Gypsum, of course, is now widely used, certainly in the UK, maybe not so much in Hong Kong, where you use concrete everywhere. But in the UK, it's widely used as in partition, as in even load-bearing walls. So this then gypsum then everywhere as lining materials of your building. So they're everywhere. What are the problems with gypsum? Well, let's then look at how gypsum performs as a fire protection material. So this is then, for example, is a piece of gypsum, and then what we have in here is then the temperature of the gypsum on the unexposed side as a function of time, in here. As you can see in here, there are two distinctive stages of temperature rise. One is this stage, where then the temperature barely increases beyond 100. 100, of course, is then the water evaporation temperature. And afterwards, then there's this stage of rapid increase because, of course, highly conductive performance of the material. So then we have to look into these aspects. The first aspect is then dealt with by specific heat. For example, if this is the specific heat as a function of temperature of the dry material, that's a gypsum. But a gypsum has a lot of water inside. In order for water to then evaporate, water then will become steam. That requires energy. It also then evaporates. That then takes energy away. What we then normally do is then to convert this process into some sort of equivalent additional energy and specific heat in the material. But of course, then this additional heat depends on how water moves around. So really, then we have to carry out combined mass, which is water movement, and heat transfer, which we did, and then we then found out how to then increase this value depending on different fire conditions. The other aspect, of course, then is thermal conductivity of the material. So if we then look at the thermal conductivity of gypsum as a function of temperature, we will find then this relationship. Start with ambient value, and then decreases, and then increases. This decrease in here, we think, which I think is quite well agreed, is because water is now disappearing from gypsum. Water is more highly conductive than air inside. So if water then is replaced by air, then the thermal conductivity decreases. And then afterwards, then the thermal conductivity increases. There is some sort of different schools of thought about why this happens. We think it is because the thermal radiation inside the bubbles. So there are a lot of bubbles, voids inside gypsum. Then as temperature increases, then radiation becomes really important, and that's then why it's increasing. So we then carried out a detailed program research to quantify these effects, and these are our prediction lines, and this dots our experiments, and then they seem to be quite good. Again, then we have published a few papers, and these are sources of information which you might be interested in reading about. Finally, about other fire protection materials, it is really then difficult to find a lot of detailed research on these materials. For example, mineral wool. But a few years ago, I searched the internet and a lot of literature as well, and then come up with quite a good set of results for various materials. And I did the systematic research, and then I found that it is possible then to provide a number of temperature-dependent models for thermal conductivity of the various materials. It is thermal conductivity which is most important, because these materials are lightweight and their specific heat values don't affect results that much. So as you can see in here, the temperature dependency is temperature to the cube. This is because radiation inside is temperature to the power 4. So if you then talk about the rate of radiation, which is equivalent thermal conductivity, then it's temperature to the power 3. Radiation becomes important because these materials have a lot of voids inside, and that makes radiation really important. In many cases, the materials have their fixed densities, but in some materials, then depending on how much air you have, then the density is different. Of course, then depending on the density, which relates the amount of bubbles you have, then the thermal conductivity values is also then also a function of density. This is how I then related them. And remarkably, by this relatively simple reasoning, I was able to find these relationships which fit remarkably well with the data which I found from the internet. And again, if you want to have more detailed information, you can then consult this book which I published with my colleagues about 10 years ago. So then we have made a lot of progress on thermal properties of the most common types of fire protection materials. But as I said, there's still challenges which need further research. So what are the challenges? Well, for intumescent coatings, one big issue, of course, is then it can crack. At the moment, when we're then testing fire protection materials, we take the average temperatures in our calculations, but average temperatures can be long since. So, for example, we have tested a piece of tubular steel, and you can see in here, these are the recorded temperatures around various locations around this piece of steel. And the temperatures in here, which of course is in this cracked area in here, is almost reaching the temperature of the fire. This is the fire temperature, and other places they're quite low. So it's been long since to then do the averaging. We really have to understand when crack happens, how do we then deal with that? Using the average is no good. So that's one big challenge. Another challenge, of course, then is related to degradation of intumescent coatings after exposure to the environmental conditions. It's not so much about sort of what is understanding them, but it's about really sort of how do we then repair and replace intumescent coatings which have degraded over time. Because it is very difficult to remove them in the first place. Even if we then remove them, we then still have to prepare the steel surface to apply new materials. So it is, of course, almost impossible to then to prepare new materials. So one possibility then is then to apply a new intumescent coating over an old intumescent coating. Well, then the difficulty is then how compatible are they? Can they then stick together? Of course, you may say, okay, I'm not going to use intumescent coating again. I'm just going to use board. Of course, you can do that. But if you want to then use new intumescent coating for replacement, then there's all sorts of issues in there to deal with. So that's then something which really hasn't been researched done. On gypsum, then there is the problem of cracking, which can happen. Of course, then when cracking happens, then this could then lead to, in the end, the whole gypsum falling down. Really, these are very, very tricky problems to understand. At the moment, it's very difficult to understand these things. We tried. It's been very difficult. Hopefully somebody can then do that. But it's really important because without understanding this phenomena, our understanding of gypsum protected steel structures or any other structure can be very difficult to predict. So that's then gypsum. I mentioned already, I said, sorry, going back. And of course, another issue with gypsum then is the variability of thermal conductivity. I have explained the basis of one model which we have used to quantify the thermal conductivity temperature relationship of gypsum. But there are very many models, there are many theories about the thermal conductivity of gypsum, why they change its function of temperature and how. And these are the models which we have collected from literature. As you can see in here, there's really a big range of values. How do we then deal with this uncertainty? Of course, which one is actually the best one, the most accurate one? But if we can't solve that problem, how do we deal with this uncertainty? That then, of course, is an issue as well. Of course, that then depends on structure you're dealing with. So there's still a lot of issues in here. So then, as a summary, thermal properties, I would argue, are the most important quantities when we're doing calculations of fire resistance of structures. More important than accuracy of structure calculations. As structure engineers, we're familiar with structure calculations, we try to do our best to make things very accurate, but we struggle. But any sort of accuracy we're trying to achieve in structural calculations may be easily overwhelmed by even small mistakes which we make in calculating temperatures of our structures. And that, of course, then comes from the wrong or inaccurate input information of thermal properties of fire protection materials. Why we're in this situation? Because there is not enough reliable data. This comes from, of course, the problem is really complicated. It's actually much more complicated than structure engineering, because the complicated behavior of the materials. And also then has been really a lack of sustained effort, research effort, because it hasn't really been as attractive or sexy as doing complicated structure engineering calculations. So how do we then move forward? I have pointed out a few directions of future research, but to progress forward, we really have to think about interdisciplinary research, because the problem is not just a structure engineering problem or fire engineering problem or a mechanics problem. It really requires collaboration between chemists, because they understand the chemistry behind, material science, because they then link chemistry with materials, and of course we need fire protection materials, which some of you are, as well as of course engineering mechanics, many of you are. So it's really an interdisciplinary research topic, and that hopefully then will be very exciting to work on. Thank you very much.
Thank you, Professor Wang. After having another 4 insightful presentations, our Q&A section will now begin. I'll pass the time to our section chairman, Engineer Professor Lee, to chair the Q&A session. And let's welcome back our speakers, Mr. Tan Wing Zheng, Professor Asif Usmani, Engineer Professor Richard K.K. Yun. As Professor Wang Yongchang is not able to join us for Q&A section today, he has prepared a video to answer some questions from our section chairman. Engineer Professor Lee, over to you.
Okay, thank you very much. And I'm Eric Lee again. And now we have the Q&A section. Next to me, we have Mr. Tam, Professor Usmani, and Professor Richard Yun. And Professor Yang Wang, because he's now in Manchester, UK, at the moment he's not able to join the Q&A. That's why I already prepared the question to him, and he replied the question by video. And we will show the video to you after the Q&A of all these speakers. So now, if you have questions, please feel free to type your question into the Q&A text box, and we'll receive it. At the moment, we received a few questions, and we'd like to reply one by one. All right, so the first question is to Mr. Tam. All right. So that is, what are the scheme owner under the PCCS? Any reference available for practitioner in the industry?
Right, scheme owner. Actually, the certification body itself can be a scheme owner for the supplier, because the supplier may like to have the COC for his product. So the certification body can be one. Also, perhaps the professional institute can be the scheme owner, because for the benefits of its members, and perhaps for the reputation and things like this, professional institute can be the scheme owner. And also, authority can be the scheme owner, because, but it will depend on the purpose of holding the scheme for what purpose. So for the we in BD, we will actually use the scheme owner, the scheme owners PCCS for the purpose. As I have mentioned, we recognize a PC product for fire door and non-load bearing partition wall. That's the start. Actually, we are considering more PCCS if they are suitable, we will accept them as well.
Okay, thank you, Mr. Tam. And the next question is also to you, Mr. Tam. All right, so Mr. Tam, two very important components in fire engineering, ASET and RSET, right? So which actually is related to MOE, yes, as FSD is involved with approval of fire engineering design. Do you think FSD should have more active role or authority in approving the mean of escape in buildings? FSD, mean of escape.
Well, let me say this. MOE is within the purview of the buildings department.
Right.
But when a fire engineering approach is used for a building or for a design, for that fire engineering approach, we must have an approval body for the design. And we have the Fire Safety Committee. And FSD is one of the members of that committee. Certainly, FSD will have much input and contribution to that committee when approving the design. So no worry. We will have their involvement in the work. Thank you.
And not only the FSD and PD, we also have professional from different bodies.
Oh, yes.
And also academics.
Yes, yes.
From Poly U, City U, Hong Kong U, right? So, okay. The next question also to you, Mr. Tam, right? The PCCS currently only cover passive fire protection products, such as fire door, blah, blah, blah. Will there be other passive material in future to be covered?
The answer is yes. Actually, if they are suitable PCCS, we will consider and adopt such scheme. For example, actually we have in our mind aluminum windows. So not necessarily fire products, but other building products.
All right.
We will consider, yes.
Thank you very much. The next question is to Professor Usmani.
Okay.
This morning, Dr. Wong, that is Dr. Yang Wong, right? He talked about the use of timber as future construction materials. Do you see this as world trend or a trend in Hong Kong?
Interesting question. I see that as not a simple question, because obviously timber is obviously a great material from an environmental perspective, obviously a sustainability perspective, and in many countries I guess it makes sense, but it also has significant issues related to fire safety. So I think, I've personally not done much work on it. I think this is a genetic problem. We have two kind of pulls. We have pulls of sustainability and environmental protection and those kind of concerns, and which is what we see in facade fires that Richard Ewan was talking about, where you have many accidents are happening because buildings have been cladded with materials that are making the buildings more energy efficient, but also they're making the buildings more dangerous in terms of like the Grenfell Tower showed, that they become a fire hazard. So I think those questions, I think for timber have not been completely answered. So I think although there is a global trend, Hong Kong obviously has a specific style of construction. We need tall buildings and stuff. So for tall buildings, timber is not used so much. There are some tall buildings in timber, very few.
Yes.
So I suspect that there are many questions to be answered in that before it becomes a global trend, or at least certainly something that's applicable to Hong Kong.
It's
in my view,
to be investigated.
In my view, yeah.
Okay.
I think there's a lot of research needed.
The next question also goes to Professor Usmani. By considering the structural failure that may caused by thermal expansion of steel, that is 550 degrees C, still be reliable figure in justifying structural safety?
So let's answer this question in this way, that basically, the way the whole point of my talk, really, or my emphasis was, the whole point of my research in the last 20 years has been really to show that the current fire safety regulations, especially relating to structural stability, are a little bit too simplistic because they are material focused. And the material where they connect structural failure to material, to the temperature of the material, and that is not a strong connection when you actually start looking at how structures really behave. So, like, I'm a structural engineer primarily, and when I look at, say, in Hong Kong, you also have typhoons, and you obviously have different parts of China. You have big earthquakes. And all the structures, when we design buildings for resisting typhoons or earthquakes, we design them to resist those forces, and they are very safe. Like in Japan, in California, we have big earthquakes, but the structures are safe because they're designed for that. In fire, we don't design; we just protect. And this is where I think we are, and that's, I think Mr. Tam talked about fire engineering approach. I think fire engineering approach is not being used enough. That's what I think, unless for buildings we actually try and understand how the structure is going to behave. There's no single answer to say the 550 degree or it may be good enough for many cases, but it will not ensure safety for some cases, and it will be wasteful for most cases. That is our experience.
Okay, thank you, Professor Usmani. There's a new question. I think this question is related to Professor Yung Wang, although he's not here at the moment, but we will convey this question to him. That is, the fire test of fire code to structural steel work by manufacturer are generally raw material, raw steel, or with some nominal primer. Would the variation of the substrate under the fire coating affect the fire performance of the fire coating? That means, he may means if we use different primer, will the fire resistant performance be changed? So that we will convey this question to Professor Yung Wang to let him to reply. So at the moment, there's no question to Professor Yun. All right, but I won't let you go, although you were my PhD supervisor. Right? I won't let you go.
Can I ask him a question?
Oh, of course.
Yes, please. Yeah, and I enjoyed Professor Yuan's talk. I just wanted to ask, because you know these facade fires you see happening very commonly. Yeah. So in that context, what do you think is the situation in Hong Kong? Are there buildings that have these kind of potential issues that are being looked at, or
well, I have not done a thorough survey, but according to my experience so far in Hong Kong, we are relatively lucky because we are in a climate where we don't need a lot of insulation for the facade, especially at the external faces. But there are certainly some of the panel, either because of aesthetic consideration or maybe some design favor of architects, they use some of those panels in Hong Kong. But I would say that with the fire problem is very dependent on firefighting techniques and firefighting strategy, as well as the other related fire regulatory controls. I would say in Hong Kong, I think it is not a severe concern because of all these combined factors. Relatively less combustible material on the facade, well-regulated fire control, and so on. So I believe it's not a serious concern at the moment.
Thank you. I have one question, Professor Yuan. Now, I can see from your presentation the CFD model is very interesting. It can simulate the fire development itself, which is quite different from industrial practice. Currently, we assume the heat release rate, we assume the fire growth, right? So is it are we oversimplified the situation of the fire development, or the result produced by this current methods? Is it reliable, or what we can do?
Yeah, well, you ask a very tricky, critical question. I have to answer very carefully. First, I think for practicing fire engineering approach has gained its merit, because you can use design tools to do prediction and estimation, but you have involved experts to analyze the result as a reference. So on that point, I would think that the current practice are good. But if you are asking for improvement, certainly I would like to see more fundamental understanding of the combustible materials being input into fire engineering approach consideration. For example, if we can nail down to the exact or the sort of material that we are burning, then certainly our fire engineering design can be taken to another new heights. This is what I would like to say. And if we can apply fire retardant in the future with the assistance of the multi-scale approach, this will add value tremendously to our design, because we may then understand the fire behavior much closer to reality, to the material that you're using, and therefore our design can go a bit beyond the certain limitation that we have at the moment, right? But having said that, building designs are very complicated. Material being used are difficult to control. So we have to apply this concept of going down to the defined material very carefully, because I'm sure that our officer will be very concerned if we go down to a certain material and we design with a certain limited margin for our fire safety, but then unfortunately when there's a fire we find that the material is different. I mean, this is a management issue, a wider scope, right?
Okay, very good answer.
Thank you.
Okay, now, although Professor Yong Wen is not here, I also won't let him go. I prepared 3 questions for him. The first question is that, Professor Wang, I'm very interested to know more about the aging problem of the insulation. As he may know that many recent commercial buildings in Hong Kong were constructed by steel structure with fire protection coating applied. All right, so I would like him to elaborate more on the degradation process of the instrumentation coating and what we can do to increase the life of the coating. That's the first question. The second question is that from his slide, I can see a rapid temperature rise after 30 minutes from the starting of the test on gypsum material. So if it was due to the high conductivity of the metal frame, can the configuration shown on slide 22 solve this problem? That is, the temperature of unexposed sides keeps gradually rising without a temperature jump. That is the second question. The third question, Professor Yong Wen, would you give some technical advice to us when we choose instrumentation coating for our steel structure, and give us few application looks of the coating? Right? These are the 3 questions. So let's see how Professor Wang replied to them.
I would like to thank Professor Eric Lee for asking questions on my presentation, Thermal Properties of Fire Protection Materials. Professor Lee asked 3 questions. The first question is concerned with instrumentation coatings. There are 2 aspects to this question. The first aspect is about the degradation process of instrumentation coatings, and the second aspect is about how to increase the life of fire protection coatings. So they'll ask these 2 questions in 10, 2 aspects of questions in 10. First, about degradation mechanisms or process. International coatings, I'm going to use a food analogy in here. International coatings are a bit like a plate of food. So a good international coating is like a plate of food with nutritious components and delicious flavors. In international coatings, there are three main components: acid source, a carbon-rich component, and a blowing agent. At temperatures of around 150 degrees, the acid source melts and reacts with the carbon-rich component, which will eventually become the char. This is then becomes a viscous liquid. In the meantime, the blowing agent decomposes and produces gases. These gases will then expand the international coating liquid, which eventually, as I said, become char. All these reactions have to happen at the right time, at the right amount, at the right rate to make sure that then the international coating is working. How to do that then? That's done by the small amount of other ingredients in the system, like the flavoring in food. The problem with international coating is then that when exposed to the environment, some of the chemicals may get lost because chemicals are reactive materials. They can then get evaporated when exposed to the temperature, to water, to dirt. So, for example, the viscous liquid then may become too viscous, which then inhibits expansion, or too liquidy, so that then the expansion will simply get burst, or there's too much blowing agent, which then creates too much pressure, or not enough blowing agent, which is not enough to expand. These are captured by these two values in the equation which I mentioned before in my main presentation, the viscosity as well as the pressure inside the system. And of course, the final char has to be quite compact, because otherwise then, if it's not compact enough, there's going to be a lot of thermal radiation within the system. And when you expose to the environment, as I say, then all these things can change because of the chemicals get lost in the environment. Returning back to my food analogy, that then is a bit like your nice, delicious plate of food with at high temperatures, or exposed to high temperatures of water or dirt, then at best loses flavor, and if it's worse, then becomes sour and disgusting, and the worst becomes poisonous or dangerous. So that's then the degradation mechanism. It is a very complicated mechanism and is irreversible, which means then once the international coatings have degraded in the environment, we can't then go back and improve the international coatings. But yet we still have to do things. What we do? Well, I put in here two aspects. One is about assessment of the residual life of international coatings. The other one is then, having done the reassessment, how do we then reinstate our structure to achieve the desired fire resistance periods of time. So looking at assessment, these methods have not been, as far as I know, been systematically researched on. I've listed three things in here which could be done. One is then conduct on-site heating fire tests, which can be done, but it's a bit difficult to implement on site. But more importantly, the results are difficult to interpret because it's very difficult or impossible to mimic the design or desirable or required heating condition on site. The second method could be then using the method which I mentioned in my main presentation by prediction. If we can then take a small amount of international coating from site and do some chemical analysis to obtain the fundamental properties for predicting its performance. This is worth doing, but hasn't been done before. Finally, you could then cut some segments or a whole section or whole member from site, from the structure, and do a fire test in furnaces. But of course, then this is very dangerous, difficult, time-consuming, expensive to do. As a last resort, maybe. So that's then looking at residual performance. And the second step is then looking at how to then making sure we still have sufficient fire resistance. One could be doing nothing. I've heard of people testing intramuscular coatings which have been used, existing for many years, still able to give us the same performance. But that's just done because the environmental condition may be very benign, not severe at all. The second one is then to match the reduced performance of intramuscular coatings with the reduced overall risk of fire, because a building is designed for a period of life, and as intramuscular coating is used for many years, then the residual total risk of the building under fire is less, proportional to the number of years, so that we can then match the residual performance of intramuscular coatings to the residual risk, total risk. Thirdly, we could overclad intramuscular coated steel members, but then of course that depends on practicality, as was also it would lose the attraction of using intramuscular coatings in the first place. And finally, we can reapply intramuscular coatings, but again, as I mentioned before, this might then be a bit difficult to do. That's the first question. The second question is about gypsum. I apologize, I may not have made this very clear in my original presentation, which then caused this confusion of this question. In my presentation, I had slide 22, which is the picture on the right-hand side, and slide 23, which is the picture on the left-hand side. These two slides were meant to just to say that gypsum, they are used, very commonly used, but they're not really directly related in terms of performance of gypsum. So the performance of gypsum on the left-hand side picture in here, where this rapid increase after about 30 minutes or around 30 minutes is not because of the use of metal in the system on the right-hand side. It's simply the performance of gypsum. This rapid increase is because of the high rate of heat flux after around 25 minutes of fire exposure, because fire is at very high temperatures, and of course also because the water has not been totally driven out of gypsum. So my main point was to say, well, this is really very critical stage of of gypsum behavior, and it's really important to have reliable thermal properties for gypsum at this stage, which is really mainly about thermal conductivity of gypsum. So that's then the second question. The final question about specification and application of intramuscular coatings. About specification, we need to talk to the manufacturers. In the UK, the information you could then find from this so-called yellow book produced by the Association of Specialist Fire Protection Manufacturers, or ASFP. The ASFP, as industry organization, has also done a lot of work about the application of intramuscular coatings, because there is the risk of somebody not using the correct intramuscular coatings and not apply them in the correct way. You could go to their website and find a lot of information about how to then apply correctly intramuscular coatings. And that is the end of my reply to the questions. Thank you.
Thank you, Engineer Professor Lee and speakers. This is a very fruitful discussion, and we are glad to have such a great panel to share their insights with our audience. Thank you very much for all the sharing. Before the end of today's symposium, may I now invite Engineer Professor Chen Xiu-Lai, Chairman of the Organizing Committee, to deliver a closing remarks to us. Engineer Professor Lee, please. Chen, please.
Thank you all for your time for the whole day seminar today. As the chairman of the organizing committee, I would like to take this opportunity to thank you all to join this HKIE Fire Division Annual Symposium 2022. The theme of this year is the fire safety performance of building material, which is to the need of the society for fire safety. Flammability and fire resistance of building elements play a very important role in the fire safety when a building is under elevated temperature. And this symposium brings us the latest technology and experience of the researchers and practitioners and regulators on the technologies about the fire performance of building elements and the tactics in managing and minimizing risk due to fire. And I trust we all have been benefit from the lectures in this symposium and will apply the knowledge to bring our society a better, a more sustainable and a safer living environment. And we are very honored to have Mr. Andy Yankin, Director of Fire Services Department, to be our guest of honor and deliver an opening address to the symposium, which is undoubtedly an inspiration to all of us. I would like to express my heartfelt thanks to all the local and overseas speakers for their effort and time, and I would like to extend my sincere thanks to all the distinguished guests and sponsors for their tremendous support, and to the members of the organizing committee for their commitment and persistent effort in spite of the difficulty under the time of the epidemics. Last but not least, thank you for your participation in making this event a success. Hope you all will find the symposium fruitful and inspiring.
Thank you, Engineer Professor Chen. We have now come to the end. Let's give a big round of applause to our guests, section chairman and speakers. Once again, thank you very much for joining us here today. I hope you all have found this event insightful and useful. See you next time. Thank you.